You can't control how big of a jerk I am, but you can control how well prepared you are. So deal with the things that you can control, because you can't control other people, not usually. Homework number 2 is due on Tuesday the 9th, and we're going to go over a couple of what I call key ideas at the beginning of our class today, just to jumpstart your ability to get through that homework set without too much trouble. In lab next Tuesday, you need to submit your report on surface tension and non-Newtonian fluids. And in the handout I gave you, I explain what I'd like for that submission. It doesn't need to be lengthy. I think that probably 1 page for the calculations and a page or 2 of discussion and observational notes would be adequate. But just read through the section at the end of that handout where I tell you what I'd like for your submission, and you'll know what to do. We'll switch the lab groups. We'll have Group B starting at 2 o'clock and Group A starting at 3 for the hydrostatic force lab that we're going to do. And I'll give you a copy of that handout in class, so if you have some time between class and the lab, you can look over it. Any questions related to these announcements? All right. Everybody has a copy of the notes, right? Let's go over some key ideas. In problem 29, it says that there's a couple of plates, and we don't know how far apart they are, but in between those 2 plates is a layer of oil acting as a lubricant. And that oil, I think they give you the viscosity of it. So we want to find out how far apart should those 2 plates be in order to limit the shear stress to 2 pounds of force per square foot. Now you'll remember from the shear stress equation that the shear stress is a function of the viscosity and the rate of strain, dV dy, rate of strain. In this case, if you assume a linear velocity distribution, then you can just substitute in the velocity into dV and the unknown gap space into dy. And it becomes a very easy problem to solve from there. Sometimes the trick with problems like this is just to sort of, in the written description or the figure they provide you, figuring out how all the pieces fit together. Another problem I wanted to show you is, this is one of my favorites from the whole semester. I love this falling cylinder problem. It's a classic. So what we have is a solid cylinder falling through a pipe. And so there's a very small gap between the 2 of them. You'll notice that the diameter of the cylinder is 100 millimeters, and the diameter of the pipe that the cylinder is falling through is 100.5 millimeters. And so there's just a really small space in between. And what we have is a lubricant in between. There's an oil, SAE 20 weight oil. And so I tell you what viscosity you should use for that at 10 degrees Celsius. There's an oil lubricating between those 2 parts, and we know the cylinder weighs 15 newtons, and in the problem statement it says derive a formula for steady rate of descent. That means steady rate of descent means equilibrium. It's not accelerating. It's reached its terminal velocity as it falls. And terminal velocity can be, if you jump out of an airplane and you're skydiving, once you get about 120 miles an hour, you don't keep accelerating on and on and on, because the drag forces that are resisting your continued acceleration are balanced by the weight that is acting downward. And so here the equilibrium is, it's falling because it has some weight of 15 newtons. It's falling through the cylinder, but the forces of the shear forces are resisting that movement. The oil is pushing up on the cylinder as the cylinder moves downward. So you've got the weight acting down and the shear forces acting up. And in equilibrium, the 2 are equal. So essentially, they want to know what's the velocity as it falls. And it's an extension of this last problem we looked at. This problem used shear stress. Does anybody remember what's the relationship between shear force and shear stress? What's the formula that relates those two, where shear force has units of newtons, shear stress has units of newtons per meter squared? How do you convert from shear stress to shear force? It's the area. Yeah, and the good hint is the units here. To get them equal, you have to multiply by the area. And so in this falling cylinder problem, there's an area that is experiencing this shear stress, the shear stress of the oil resisting its movement. So some of the key things to think about as you solve this problem is what is the magnitude of the forces and what directions are they acting? And what direction is the weight acting? And what direction is the shear force of the liquid acting? Calculating the magnitude of the shear force is just multiplying the area by the shear stress, or the area times viscosity and the rate of strain, du dy, where u is interchangeable with v. They're both velocities. The question is what area, and I'd say the most common mistake on this problem is that someone will say, well, it's the area here. But that's not the area that governs the resistance. It's the area that this cylinder is in contact, well, almost in contact with the shaft that it's falling through. And so you have to also consider the gap distance. And you know that there's two diameters listed there. There's the diameter of the cylinder and the diameter of the pipe that it's falling through. And so you have to calculate how close together are the pipe and the cylinder. What's the gap distance, in other words, between them? Because that's going to function into the dy. Okay, we've got a problem with a bug, and this is a surface tension problem. It says that there's a 6-legged bug. Each leg is 5 millimeters, and what's the maximum mass before it falls through the surface? And we know that the surface tension can be looked up. It's a fluid property that's a function of temperature. So you can look up sigma. And if you know sigma and multiply it by some length, that'll tell you the force of the surface tension force acting upward. So in equilibrium, they're asking what's the maximum weight that is equal to the shear force, not the shear force, the surface tension force that the bug is causing to exist as it lands on the surface there. And one thing to point out is if we look at a cutaway of the bug's leg, there's actually 2 contact surfaces as it lands on the water. There's one on each side. So our formula here asks us to find some length. But it's not just going to be 6 times 5 as the length, because on either side of the bug's leg, it's in contact with the liquid. And so you need to account for both sides of the leg when calculating the total length that's in contact with the liquid. That's the tip that I wanted to give you on that one. All right. And finally, this is the Sutherlands equation. You can find it in the textbook, but I thought I'd mention it because you have a problem that goes along with Sutherland's equation. It's a method of estimating the viscosity of a gas as the temperature varies. And Sutherland's equation is here, and it says that the viscosity of a gas at a known temperature, so the original viscosity and the original temperature, you can find the viscosity at some unknown temperature by using this formula. So if you're given the viscosity of air at 10 Celsius, you know the viscosity and the temperature, and you know the Sutherland's constant is 111 Kelvin, you'll need to first of all convert the temperature that you have into Kelvin so that it's consistent with the units of Sutherland's constant. And then the unknown temperature is what you'd substitute in for T, and you can find the viscosity from that. You've got a problem in your homework that asks, it gives you the viscosity of air at one temperature and wants you to find it at the other, and this is the formula that you'll use for that. There may be occasions where We don't have time in class to cover every concept in the text, and so if you come across something unfamiliar, like if we hadn't talked about Sutherland's equation in class, you just go to the index of the book, look up Sutherland's equation, the unfamiliar thing, and there it'll tell you what page the formula is on. So don't panic if you see a phrase or a concept that we didn't talk about in class or have an opportunity to go through and do an example on. I'll try and do as many examples as we've got time for, but occasionally there may be a concept or two that you have to look in the text to be able to figure it out. The main thing that we're going to talk about today is vapor pressure and what's going on here. What is this a picture of? It's boiling water, and at sea level, water boils at 100 degrees Celsius. But water boils at a different temperature at other elevations. For example, at the top of Mount Everest, if someone took the trouble of lugging extra water up there and lighting a fire and trying to get it to boil, the water would boil at 69 degrees Celsius at the top of Mount Everest. And so we know Mount Everest is very high, but what is it about Mount Everest that causes water to boil at a different temperature? Is it because it's like a mystical, special place and it's like magic is happening, or is there a physical explanation? Atmospheric pressure at Mount Everest, at the top of Mount Everest, is what? It's less than atmospheric pressure here. As you go up through the Earth's atmosphere, there's less gas because of gravity, actually. Gravity keeps a greater mass of gas molecules at the surface. Then there's less gravity as you go up, so the pressure decreases as you go upward through the Earth's atmosphere. And so the water boils more easily is the way you can think about it. And if we were to draw a little diagram of what's happening in that kettle as the water boils, here's our container, and here's the water surface. It's open to the atmosphere. When you heat it up, initially when it's at room temperature, the water molecules are trying to escape. They're trying to get into the air. They're going from the liquid phase to the gas phase, but they're not putting a lot of effort into it. The atmospheric pressure at sea level is pretty high. And so just in a conceptual basis, what we can think of is that the gas is resisting the escape of the liquid molecules. Liquid molecules have kinetic energy. They're moving around, and as you increase the temperature of the liquid, those molecules move around more. And if there are two molecules that are moving around and they bump into each other, that collision transfers some of the kinetic energy from one molecule to the next. And so then there will be just some stray molecule that has a lot of energy, and it's got enough energy to make it through that liquid-gas interface. We know that there's a membrane effect because of surface tension, and that's part of the reason why it's difficult for a liquid to escape. But all liquids have what's called a vapor pressure, and that is, you can think of it as how volatile the liquid is. Gasoline, for example, or alcohol has a very high vapor pressure, and you've probably noticed that if you spill gasoline, it evaporates really quickly. And that's because the molecules of that liquid have a high tendency to vaporize, and it doesn't require very much kinetic energy to get them to go into the gas phase. But what we're doing when we add heat, we're increasing the pressure of the liquid, the vapor pressure, increasing how much energy that those molecules have, and the random collisions are happening more often, and a greater number of those molecules are able to achieve the energy level required to make it through the interface as you heat up the liquid. So we can think of vapor pressure as the pressure at which a liquid will boil. And it has a temperature component. The vapor pressure increases when temperature increases. And so I lengthened these arrows in the drawing on the board. I made them longer when I said we were heating it up. Originally, if it's just room temperature, there isn't very much vapor pressure because there isn't very much kinetic energy. But if I have a little candle going, and there's flames and there's heat, then that's going to increase the kinetic energy, increases the vapor pressure, and the liquid is more apt to change into a gas. And so this figure that I've just put on the screen is showing the relationship between temperature and vapor pressure for water. And the units of pressure that are listed here is millimeters of mercury. And you may remember from your days in chemistry that atmospheric pressure is 760 millimeters of mercury. That's atmospheric pressure. So it's no coincidence that water has a vapor pressure of 760 at 100 degrees Celsius. That's by definition. The way that they decided what is 100 Celsius, they said that is the temperature at which water boils. And so 100 Celsius is the temperature that water boils, and 760 millimeters of mercury is atmospheric pressure. And so when atmospheric pressure equals the vapor pressure of the liquid, that's when that liquid will start to boil. You'll notice that the vapor pressure decreases as temperature goes down. But it doesn't go to zero at 0 Celsius. And actually, even when water is frozen, it still has a vapor pressure. When it's in the solid state, you can have something like a block of ice will evaporate without having to melt first. And that process is called sublimation, which is when something goes directly from the solid phase into the gas phase. It doesn't happen very quickly. You can think of these vapor pressures as how quickly something will evaporate. Because even before water boils, if you take it up to 80 Celsius, it's going to evaporate a lot more quickly at 80 Celsius than it will at 20 Celsius, because a greater fraction of the molecules have what it takes to go into the gas phase. So here is a graphical representation of vapor pressure, and you can see it's nonlinear. That one of the things that I do, one of my hobbies, is boiling maple syrup. I've got some maple trees on my property, and so starting in January, I'll go from tree to tree every night when I get home from work, and I'll pour the sap from a bucket. I drill holes in the trees, and a little drop of water comes out, and I collect it in a bucket. And then on the weekend, I'll boil all of that sap, and you have to boil 50 gallons of sap to get 1 gallon of syrup. It requires a lot of energy to do. But if I heated the water up, if I heat the sap up to 80 Celsius, it's not going to evaporate very quickly because its vapor pressure isn't high. It's worth it to me to get it up to 100 Celsius because by just increasing it 20 Celsius, I get a much higher vapor pressure, and it'll evaporate a lot faster. Now, there's two ways to boil water. And one of them is by adding heat, and the other is by removing pressure from above the water. So remember, when we have room temperature water, when I'm not heating it, then the vapor pressure is low. What if I enclose this system into a container and I start pumping out the air? I pump out the atmosphere, and so the gas pressure is going to be decreasing and decreasing, and when the two are equal, when the gas pressure above the liquid is equal to the vapor pressure, so when P sub V is equal to the pressure of the atmosphere that surrounds the liquid, then it will start to boil, regardless of how you got there. So there's two ways to make these equal. You can either increase the vapor pressure or decrease the atmospheric pressure. All right, and the video that I want to show you for that is here. I crashed PowerPoint earlier today by trying to show a video. We'll see if it makes it through unscathed this time. Heavy lifting. There, oh,
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards pump. By using and applying vacuum, we're making water change from liquid to vapor very quickly and very effectively. Water at room temperature is placed into a beaker before putting it into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces. And as the pressure becomes lower, the water will eventually freeze. You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food packaging industries.
So we didn't really talk about, before showing that video, why it froze. But the reason why it froze is that as evaporation occurs, so does cooling. You know, when your body sweats, it's sweating to cool you off. And so the process of a liquid going into the gas phase, your sweat vaporizes, and as it goes through that process, it steals heat. And so what we were seeing there is that they weren't adding heat to get it to boil. They were reducing the pressure surrounding it. But then as it was boiling, the liquid was actually cooling off. And then it finally froze. So that was a pretty interesting demo. Any questions about what we just saw? Here is a table taken from your textbook that is showing the density and specific weight and viscosity and also vapor pressure. And here, this column is showing vapor pressure in terms of pascals. The chart that I showed you before was in terms of millimeters of mercury. Here it's pascal. And 101, 300 is atmospheric pressure corresponding to 100 degrees Celsius. One of the reasons that that vapor pressure is important, one application of fluid mechanics, just to give you a peek into the more engineering side of this course, cavitation is another word for boiling liquid. And cavitation is what we call it when a liquid boils because the pressure decreased rather than because heat was added. So cavitation is liquid boiling, and I'm going to put vaporizing because the surrounding pressure decreased. In our minds, we may just sort of instinctively think of boiling as something associated with added heat, but that's not always true. It's either added heat or a reduction in pressure. Cavitation specifically is the process of a liquid going to the vapor phase when pressure surrounding the liquid goes down. So what we just saw was an example of cavitation. There are other examples of cavitation. In the Navy, sounds like I'm about to start singing a song, right? Like, I'm not. In the Navy, there's submarines, and they've got a propeller at the end of the submarine. They're underwater, and they need to stay quiet. because they don't want anyone to know where they're at. They could be stealthy, so they could sneak up on other ships and sink them. Or if it's a nuclear ballistic missile submarine, they want to. The deterrence depends on nobody knowing where the submarine is, and so it needs to be quiet. If a submarine accelerates too quickly, then on the backside of the propeller, the pressures decrease and cavitation occurs. And so submarines can't go from stop to full speed without experiencing cavitation. And cavitation is very noisy because what you're having in cavitation is a liquid going to the vapor phase. So little bubbles form, and then those little bubbles will collapse, and it's a really noisy kind of a swirling sound that gives away a submarine's position very easily. And so to avoid cavitation, submarines have to accelerate gradually. Another instance where cavitation is important is in pumps and in hydroelectric dams. And this is a sort of a case study in Russia of a very large hydroelectric dam, one of the largest in Russia. It provided electricity for aluminum smelting, a lot of heavy industry, a very important dam that had 10 generators. And you can see that the way this was working is the water that's behind the dam is at a high elevation. So we don't see it, but behind that dam the water level's up to about here. And because the water level's so high, the water will go through these pipes and then it spins a turbine as it's falling through that pipe. And the spinning turbine generates electricity. The problem is that one of the turbines that was spinning started experiencing cavitation. And so these little air bubbles were forming. And the cavitation can, as the little vapor bubble collapses, it sends a shock wave through the water, and it can cause pitting or erosion of the steel in the turbine blade. And so it started wobbling. The turbine started wobbling, and people think that its vibrations and its imbalance is probably because there was pitting and cavitation damage of the impeller that was spinning around. And this is ultimately what happened at the power station. More than 70 people who were on duty died because one of these power units became imbalanced. It shook apart, came up out of the floor, and so did a bunch of water. And so more than 70 people drowned, and they did a multi-year investigation. It took a lot of effort to figure out what went wrong. And 9 out of the 10 turbines that were there were completely destroyed. It threw the local economy in this region into basically collapse because there wasn't enough electricity available. So all of the metal processing had to be done with diesel generators, which is like 10 to 20 times more expensive to produce electricity with diesel than with a hydroelectric station where all you're doing is harnessing nature's power. So it caused a lot of problem, and we're going to talk in hydraulic engineering how you can avoid the risk of cavitation when you're designing. Because one of the things that can cause cavitation, besides a hydroelectric power or a quickly accelerating submarine, is pumping water, sucking it out of a reservoir. If you have a tank of water and here's a pump, and you put your pipe down into the tank because you want to lift it and start spraying it somewhere. If this pipe is too long, or if there's too much of an elevation difference between the pump and the water surface, that can also cause cavitation, and it can break the pump over time. So we'll talk all about that. But it's one of the interesting applications of vapor pressure, is that liquid that has a high vapor pressure is going to be more prone to cavitation. So hot liquids, liquids like alcohol, gasoline, kerosene, those liquids, you have to be even more careful when you're pumping them because they're more prone to cavitation than water is. Okay, so that concludes the part that we're going to be talking about for vapor pressure, and we're going to begin talking about pressure and hydrostatics. Hydrostatics is the remainder of Chapter 3, we're going to be talking about forces on flat surfaces and forces on curved surfaces. And before we can talk about those forces, we have to understand pressure a little bit more. Pressure intensity is the phrase that's used to actually describe pressure, because pressure is a scalar, meaning that it doesn't have direction. It acts in all directions. And so it's pressure intensity rather than just pressure, but we abbreviate it and call it pressure. In the SI system, the units are force per unit area in traditional, and so that's newtons per meter or Pascal. In traditional, it could be pounds force per cubic foot or per square foot or per square inch. And like I said before, it acts in it acts in all directions equally rather than in one direction. So if you go down to the bottom of the ocean and you turn your head around, it's not like you can shield your ears from pressure. If you're swimming and your ears start to hurt, you can't look sideways and take the weight of the water off of your ears. It's acting in all directions equally. And so with having said that, which one of these do you think has a greater pressure at the bottom? The reservoir on the left, which is smaller and there isn't as much water in the reservoir on the left, or the reservoir on the right, which has a lot more. They're the mirror image of each other, but the reservoir on the right is much wider. So if you're at the bottom of each reservoir, how do the pressures compare? Same. That's a trick question. It's the same because it only matters, the pressure at the bottom only matters how much water is above, not how much water is to the side. Pressure only depends on the column of water above some point in question. So it's acting equally in all directions. The implication of that is it doesn't matter if if you go scuba diving and you want to get certified, you can get certified at a certain depth in a cave or in the ocean, but as long as it's the same depth under the water surface, the pressures will be the same. And so you'll have the same considerations with mixing gases and all those sorts of things. The hydrostatic equation is the relationship between depth and pressure. So dP dz. Pressure is the variable P, and elevation is the variable Z. And so what it says is here we're going to use the bottom of some tank as our elevation datum. And as we go up through the liquid, the pressure decreases. That's why there's the negative sign here in the expression. Does anybody remember what the name of gamma is, the variable? What do we call that variable that's expressed by the symbol gamma? Specific weight? That's right. Or we sometimes call it unit weight. Either one is okay. And what we know is that for water, the specific weight is 9810 newtons per meter cubed. What this hydrostatic equation is saying is that this is the rate of pressure accumulation or reduction. So in the tank that's shown on the screen here, if we're at the bottom of the tank and we start going up, every meter that we go up is going to reduce the pressure by 9810 newtons per meter squared. And so dP, or the change in pressure, is going to be dz times the unit weight, and there will be a negative sign there because the pressure is decreasing as the elevation is increasing. So we can think about it that the pressure is going down as elevation goes up, or if we're at the surface, if we're at the top, then the pressure at the surface, I alluded to this in our last class period, that if it's open to the atmosphere, so if it's got the little triangle and these hatch marks, that tells us that there's air and that it's not sealed off. So if it's open to the air, then the water at the interface has the same pressure as the air immediately above it. But if we start going down, then pressure is going to be accumulating, and so it's going to be accumulating at the rate of gamma. 9810 newtons per meter squared for every meter that we go down. So 9810 pascals per meter of depth. That's the rate of pressure accumulation. And from a units perspective, that should make sense because dP, pressure, has units of newtons per meter squared. And if we divide that by units that are associated with elevation, dz, that'll be meters. So newtons per meter squared divided by meters gives us newtons per meter cubed, which is the units for unit weight or specific weight. There's so many problems you can solve with this easy equation. It's really remarkable how powerful that is and how many different ways we're able to apply it. Now there are some considerations here. We assume that water has uniform density as we move up and down through a column of water or some other liquid. It's not always water. For liquids, that's a pretty good assumption, but for gases, it's not the best assumption because remember earlier just today I said that the pressure at Mount Everest is lower than the pressure at sea level. So air is a liquid. We can use the hydrostatic equation to find out what is the pressure at some elevation, but the problem with applying that for too great of a vertical distance through a gas is that the density of the gas is lower at a higher elevation than it is at a lower elevation. In liquids, that's less of an issue. We can integrate the hydrostatic equation to get something called piezometric pressure. And piezometric pressure is the sum of the pressure and some expression of the effective elevation above a datum. Z is the elevation above a datum. Or we can express it another way in terms of piezometric head. So let me just show you what I mean by piezometric pressure. Let's say that we are here at location 1. We're down under the surface some distance. We can find the piezometric pressure there by defining a datum. If we say the bottom of the tank is our reference point, Z datum means this is our reference point. And it's a reference point for measuring elevation. We're going to measure all of our Z values upward from the bottom of the tank. I can find the piezometric pressure here at 1. Piezometric pressure is the pressure P, so that accounts for how much liquid is above it. And then the gamma times Z accounts for how much liquid is below it between the point in question and the datum, the reference point. So piezometric pressure is using elevation as one of the factors. And if we divide each term by gamma, so if we divide pressure divided by gamma and gamma Z divided by gamma, then we get this in terms of piezometric head instead of piezometric pressure. Piezometric pressure, the units of each of these terms is going to be newtons per meter squared. And so pressure we already know is newtons per meter squared. Gamma Z is newtons per meter squared because the gamma is newtons per meter cubed, and then we multiply it by Z, which has units of meters. So if we want to express it this other way, both of these terms will have units of length. Z has units of length, and pressure divided by gamma will have units of length as well. It's a constant in a liquid. Piezometric pressure and piezometric head are constant, which means here in this tank, if I go from 1 to 2, there is not going to be any loss in piezometric pressure or piezometric head. I mean, the pressure will be different, but piezometric pressure accounts for not only a change in pressure, but also the change in Z. So if we compare 1 versus 2, Location 1 has more P because it's deeper under the water. So the pressure at 1 will be greater. But location 2 has more Z. And so if we travel from 1 to 2, we're going upward through the column. We're gaining Z and losing pressure. Anywhere in a static fluid, the piezometric head and the piezometric pressure are constant in a static fluid. When the water starts moving, it's not constant, but as long as you've got hydrostatic conditions, this hydrostatic equation can tell you how pressure changes between 2 points. So this is another way of saying it, is that I can compare the pressure at 1 and the pressure at 2 by knowing the elevation of each of these points. And so I can find out, if I know the pressure at 1 and pressure at 2 is unknown, I can find out what is the pressure at 2 by accounting for the difference in elevation, the different Z's. So let's apply that with an example. We want to find out what's the pressure at 2. Actually, why don't you work on this with a colleague, and then when you got a couple minutes of a head start, I'll jump in and start writing the solution on the board. We're not too pressed for time today, so I think you've got time to take a first crack at this without just watching me do it on the board. So we start off by writing the hydrostatic equation. We know that the pressure is given at 1, but the pressure is not known at 2. With the hydrostatic equation, it doesn't matter what you call 1 and what you call 2. Later on in the semester, we're going to have conventions where, you know, you have to pick the higher fluid and call that number 2, and number 1 will be the lower fluid. But here in the hydrostatic, there isn't any such consideration. So I said 1 is 66,000, Z1 is 34, we know Z2 is 26. So rearranging the hydrostatic equation to solve for P2, and then substituting in the data we've got is 144,480 newtons per meter squared. And then I abbreviate that to 144 kPa. Kilopascals. Yeah.
Do you always want to condense?
I'm not picky. You mean always use kilopascals?
Yeah.
No, not necessarily. No. But what you sometimes have to think about is how precise is the data that you started with. For example, we're told that the elevation here is 26 meters. It didn't say the elevation is 26.00000 meters. So, I mean, I probably can't have all these levels of precision, all these extra digits here, and assume that it's actually going to be that accurate of what the pressure is at 2. And so even if you left it in terms of pascals instead of kilopascals, it would probably be more accurate to say that the pressure is going to be 144,000 newtons per meter squared rather than 144,480, because the data we started with doesn't justify claiming 1, 2, 3, 4, 5 digits of precision. All right, other questions? That's a good question. Hydrostatic equation is pretty simple, and actually there's even a simpler way that we can do it. Instead of having the hydrostatic equation the full way, we can abbreviate it when we're interested in calculating the change in pressure between 2 points. The change in pressure depends on the vertical distance between them, delta H, and the unit weight of the fluid, gamma. So let's go back to this one we just worked. What is the delta H in this problem? Between 26 and 34, I'm going to work this the other way now. So delta H is 34 meters minus 26 meters. So that distance is going to be 8 meters. So the delta P is simply going to be the delta H multiplied by the unit weight. So the delta P between the 2 points, the pressure change is going to be unit weight times delta H. So it'll be 9810 newtons per meter cubed times 8 meters elevation difference. So the delta P, anybody with a calculator do that calculation real quick? 78,480 newtons per meter squared. And so the way that we find P2 is we'd say P2 is P1 plus delta P. We know just by looking at it that the pressure at 2 is going to be bigger because it's down deeper in the fluid. So it'll be the starting pressure that you had of 66,000 pascals plus adding 78,480 pascals, and together that total pressure is 144,480 pascals, or 144 kPa. So if it's just the change that you're interested in calculating, then this other approach is a nice way to do that. And I ask, what's the pressure at the bottom of Challenger Deep if we've got this known depth and it's seawater, which has a slightly different unit weight than freshwater. The unit weight of seawater is even greater. So in terms of pascals, what should be the pressure at the bottom of the Mariana Trench? Challenger Deep. So we have delta P is delta H times gamma. And here our delta H is 10,911 meters. And the unit weight of seawater is 10,100 newtons per meter cubed. And so, let's see, did I do that one? No. Let's calculate it. 10,911 meters, 10,100. Okay, so that is 110.2 megapascals. It's really high. Any questions about the hydrostatic equation? So what should you be doing between now and Tuesday? You should finish homework 2B and then also your lab report. I've got office hours today starting now through 3:30 and then also tomorrow morning. If you've got any questions, feel free to stop by. I'll see you on Tuesday.